Hey guys, this is GKCS. We are talking about one of my favorite topics today, which is non-polynomial problems or challenge problems. So, challenge problems are something that you've probably heard from in Codechef or HackerEarth. I'll just explain this using an example. Imagine you have been given a problem to solve like the traveling salesman problem. Okay, so the traveling salesman problem is very well known in computer science. And to get the optimal solution to this, it's known that the problem is NP, non-polynomial. So the optimal solution, it takes around n square into 2 raised to power n time. So this is exponential, and therefore the running time is non-polynomial. Okay, so you're seeing that to get an optimal solution, you need non-polynomial time. Now contests will ask you to run your code within 1 second or 2 seconds. So assuming that they're asking you to run the code within 1 second, for you to meet this 1 second time limit, you need n to be around 15. So n has to be around 15 for this code to run within 1 second. Now what happens if I give you n equal to 1000? There is no chance that you can run this code and get an optimal solution within 1 second because it's been proven to be non-polynomial running time. So the only option you have is to use some other algorithm, which is, let's say, n is equal to 1000. So for it to run within 1 second, you will need something like an n square algorithm. Okay, but we have already said that there is no chance that you can get the optimal solution. So what these contests ask you to do is sacrifice optimality for performance. Okay. Give me an approximate solution, that's very important, approximate solution within 1 second, so that in a reasonable time, and the better your approximation is, the more you score in this problem. So the scores go from 100 to 0. 0 is basically wrong answer. And if your solution is good, I mean, if it is the best, then you get 100. If it is close to the best, then you get around 90s, 80s, 70s, and if it's the further away you are from the best solution, the lesser your score is. And so basically what you want to do is maximize your score, in which case you want to make your approximation as close to the optimal solution as you can. Okay, within the 1 second time limit. So we are going to be discussing how to solve these kind of problems, which are actually very interesting because as you'll see, we'll be using all the resources which are given to us with an example. So the example problem that we are going to pick up is CN2. Okay, this is mentioned in the description below. You can have a look at it later on. But I'll just explain what the problem says. You have an array given to you, and it's called B. Okay, so this is the array B, and there's a number given to you, which is A. A is a number, B is an array. B has, of course, integers in each of these positions. So B of 0 is some number x, B of 1 is some number y, and so on and so forth. What your job is to do is to minimize the sum of all remainders that you get from A after dividing with all the numbers in B. So mathematically it's easier to express it as, for all numbers in B, let's say the size of B is equal to n. So I equal to 0 to n minus 1, you need to find the remainders of A when divided by B of I. Okay, and you need to minimize that. It's pretty simple. And the only operation you are allowed to do is to take all the digits of A. Okay, so A is, I think, 18 digits, approximately 10 raised to the power 18 was the size of A. And you can permute them. So after permuting them, you just assign it back to A. So A can be any permutation of its digits. And then you run it through this function with the intention of minimizing this quantity as much as you can. So the lesser this quantity is, the higher your score is. The more this quantity is, the lower your score is. Okay. And for example, let's take A to be 3941. Then a valid permutation of its digits is going to be 9134. another valid permutation is 4193. Okay, so all these permutations are valid. You need to just print out the permutation which is according to you, reducing this quantity as much as you can. All right. So, any ideas? In the start, this might look like a proper question where there's a standard polynomial algorithm that you can apply and you can get the minima. But the more you look into this problem, you see that no, that's not possible. This is an NP-complete problem, and the only way to actually get a solution in a reasonable amount of time is to use an approximate algorithm. Of course, in a contest, you don't need to do all that. You don't need to do all that thinking because the problem is already declared as a challenge problem, and you have partial scoring from 0 to 100. Okay, but again, what are the ideas? The structured approach to actually solving these problems is to look for a base solution. Okay, you want something to start off with, and over here, actually, the easiest thing to start off with is the input itself, A. You can take A and you can find what the current answer is giving you. You know, if you just take the input A and you run it through this function, what is the answer? So this is, let's say, 30. And then what you can do is, because you have valid permutations to look at, instead of permuting the whole array, what you can do is you can swap two integers, two elements at different positions, of course. Once you have swapped them, so let's say I swap 1 with 3. So that gives me 4931. And if my answer changes suddenly to 35, that gives me an idea that this swap was not nice because I'm looking to minimize. On the other hand, if I swap and I get the answer to be 25, that gives me an idea that this swap was a good idea and I should continue with this new number as my base case. Okay, so first thing to do is find a base solution. So after you have a base solution with which you can compare your next answers, what you want to do is you want to improve on the base solution. So let's take this graph to be the values of A and the x-axis and the score that you are having. So the minimize some function f of A, right? That's what you're doing. So f of A is plotted on the y-axis, A is plotted on the x-axis, and what you want to do is find the minima. This seems pretty nice and pretty simple. Now you cannot take all the possible values of A because there are 18 digits there, and in a trivial way that will be 18 factorial possible values. So this graph has 18 factorial possible values. You cannot try all of them, and therefore you are limited to the number of points that you can plot on this graph. Let's say that you start plotting points like this. For a low value of A, you got something like this over here. For the next value, you got something lesser in f of A. For the next value, you got something really high, and then much smaller, and then somewhere over here, over here, over here, here. So you're seeing that my drawing skills are terrible, but apart from that, what you're seeing is these points represent the different values that you plotted for different values of A. For this function and this value of A. Fine. Now, these points in general, they don't make any sense. But what you try to do then is plot a graph out of these. So if I start plotting a graph, one of the things I can do is just join the points, but that also won't really help us in understanding what's happened. So we try to fit a curve. Okay, we try to fit this curve, and all of you who are interested in data science must be getting many ideas by now. So this is the curve that I just fit, and it looks a little sensible. It seems almost periodic in some way. I don't know what we can infer from this, but one of the things we can infer is that this is the minima. So it makes sense to search around the minima instead of searching around over here. Okay. So if this is the minimum value, this will be your final answer also. But instead of investing time over here or over here, you want to invest more time over here or over here. That's a general idea of finding the minima in a curve. You want to define a function and you want to find the minima. Alright? So there are many approaches to this. The second part is basically something like curve fitting. And because you have many approaches, I'll just mention a few. One of them is hill climbing, okay, which is probably the most common one. Something which is again very, very common is an evolutionary algorithm, which is simulated annealing. And finally, something that I really like and is also very popular is genetic algorithms. In general, what these problems are doing, what these algorithms are doing, is trying to fit a curve to the search space, and in this search space, then find you the maxima or the minima. So our requirement is minima, therefore we are finding minimas. But have we been searching for maximas? This would have been an interesting place. This would have been an interesting place, and even the far end. So basically, what we are trying to do is we are trying to then find we are trying to define the function that we are getting by plotting points a and f of a, and we are trying to get what we want, which is the minima or the maxima. Taking the example that we are talking about, the array b and the integer a, using simulated annealing, which is one of the techniques that you can use, here's how I would do it. You have the array b, which you cannot change, so there's nothing to do over there. You have the number a, which you can change. So initially, I have a base case, which is the input itself. The input gives me a itself. What I'm going to do initially is try to find random permutations of a, okay, different permutations of a, and I'm just going to run them through the function f of a for different permutations. Now you'll see that different permutations will give me different answers, but the answers which are lesser and lesser, which are minimizing the final quantity f of a, are the ones that I'll give more preference to. Okay, so that's how it goes. There are many possible values of a. Let's say I have a set, capital A, and in that, or I'll just call this set small a. Okay, and in that I have many values of a, a1, a2, a3. All these give me corresponding values of f of a1, f of a2, so on and so forth. Initially, I'm just finding all the permutations that I can and trying to find some answers for them. In the next cycle, okay, so there's a concept of cycles in this. In the next cycle, what's going to happen is I'm going to give more preference to smaller values of f of a. So I'll pick those guys up. Let's say they're a2, a7, a9, a20, so on and so forth. And then I'll run the same thing, but not with such an aggressive mode. I'm not going to find random permutations now. I'm going to take these numbers and I'm going to swap just, let's say, 2 digits in those numbers. So if this is the number, a of 0, a of 1, in terms of their digits, then I'm just going to take 2 digits and 2 other digits and swap them. Okay. Swapping will generate a different number, a different permutation, and that will be what happens in the second cycle. Again, correspondingly, f of a will be there. So f of a2, f of a7, and so on and so forth. Mind you that a2 and a7 will change after these swaps. In the third cycle, I'll take an even less aggressive approach because my solutions are getting better and better and better. Of course, I'll not choose poor solutions from this experiment of swapping 2 numbers. So I'll get an even better crop. You can think of that, a better version of A's, and I'll swap just 1 digit now. So instead of swapping 2 digits, I'm swapping just 1 digit. And this is the basic understanding of what simulated annealing is. Simulated annealing means annealing. So initially, when you have some hot metal and you want to bang it into shape, what happens is initially all the atoms are jumping around, trying to find stability. And as the temperature goes down, which is basically as time passes by, the number of the atoms have found the stability and they stay right there. The ones which haven't found the stability also reduce their exploration. Alright, you can read up on simulated annealing in the description below the link. But in general, starting, you explore as much as you can. don't care about stability so much. Later on, when you get better and better solutions, keep them in your hand. Keep that stability in your hand and look for slightly better solutions. So finally, in terms of how it will look in the graph. So if this is your curve and you're looking for minimas, initially you don't even care if you jump up to this point or these points or these points. Later on, what will happen is that you want to save these points, the minimas, and then search over here itself. So if you're somewhere over here, you want to go slightly lower. Now, if you go to the left, you discourage that. If you go to the right, you encourage that, but not enough. So you go slightly better, and then slightly better, and then finally to the minima maybe. That's the general idea of simulated annealing. So you're seeing that all of these algorithms actually help you find the minima or the maxima in the curve using common sense, using logic. Okay, common sense logic, yeah. But yeah, that's what they are actually. And genetic algorithms are a little involved, so that's why I didn't want to speak about that. But I have implemented that in one of the contests, and it worked out really well. So you should try for different problems, different approaches. The third part is actually my favorite, which is optimization. So I think it's the favorite of most computer programmers also. Optimizing a solution so that it runs the fastest possible. But in these kind of problems, actually, it's very, very important, optimization. Even if you have a good enough solution, what these problems are saying is that you have an approximate solution. And so if you have the same algorithm with the same parameters, the person who can use more CPU, the person who works harder, will have a better approximation. Okay, that's what it means. So what you need to do, even if you have a good solution and if you have reasonable base case solutions and you've done something really smart, the more CPU you use, the better your solution will be. And therefore, what you want to do is you want to improve your approximation through optimization. So how do you do that? The first thing that you want to do is, if the input is really small, if, like we said in the traveling salesman problem, if n is equal to 15, then you can get the optimal solution through brute force. The first thing you want to do is brute force small solutions. Alright, this is obvious, and I think some of the contests don't even have small inputs, so you can even ignore this maybe. The second thing you want to do is utilize as much time as you can. 1 second is the time limit, utilize all of it. 1 second time limit, basically utilize time. Now, how do you do this? In terms of Java, what you can do is you can just check the system time initially when the algorithm starts, and every time you're running a new iteration of the algorithm, check from the system time to the current time. If the difference is more than the time limit, 1 second, let's say, then you need to terminate the algorithm and print out the best answer till now. Okay, so utilize your time, which is as much as you can. The final one is the most exciting one, which is domain specific searching. Right, domain specific searching basically means using the problem statement, finding some interesting patterns in the problem to get a better solution. Alright, so taking the problem that we were talking about earlier, B is the array given to you, right? And you need to divide A by all integers in B and then find the minimum. In this case, what are the remainders from the numbers in B? So let's say the first one gives you remainder 0, the second one gives you remainder 1, and so on and so forth. So you'll have to take the sum of all these remainders. On average, in a brute force, not even a brute force, in a random permutation of A, what is the expected remainder being given by rem0? The expectation is that it's going to be B of 0 by 2. Why? Because the remainder will range from 0 to B of 0. Okay, the second remainder will range from 0 to B of 1. The third remainder will range from 0 to B of 2, and so on and so forth. So, if I take an even simpler example, if I divide a number by 5, approximately I'll be getting 2 as a remainder, because 0, 1, 2, 3, and 4 are the possible remainders. I can pick up the center one. Okay, so in this case, the the expected remainder is b of 0 by 2. For the next one, it will be b of 1 by 2. For the next one, it will be b of 2 by 2. And because I'm taking the sum of all these things, the expected sum out of these is going to be half into b0 plus b1 plus b2, so on and so forth. Alright, which in turn tells me that the expected is this quantity, right? If b is an array which is uniformly distributed and random, okay, this is important. If you find uniform distribution and it is random, then what you can say is that you have n numbers in this array B. I'm going slow purposely so that it's easy to understand. N numbers in B, uniform distribution. What I can expect in general is that the numbers will be something like 1, 2, 3, 4, 5, up to n. Okay, that makes sense. That's an expectation. None of these are guarantees, by the way, but expectations. In this set of numbers, which are the ones which will impact your answer the most? Because you're taking the sum of all remainders, which are the numbers which will impact your answer the most? It will be these numbers, the larger numbers. The smaller numbers can be almost ignored. And I can prove that to you mathematically. You're taking the sum of approximately all bi. That's the expected. So bi by 2, half of this. So your job is to minimize this quantity. And to do that, what you're going to do is you want to focus on the larger numbers. That's what he said. So the numbers in uniform distribution are going to be something like 1, 2, 3, 4, 5, 6, so on and so forth. This gives you up to n. So the sum of all the natural numbers is going to be this quantity, n into n plus 1 by 2. So expected answer is going to be something like this. And if I take just the first 30% of the numbers, it's going to be n by 3 into n by 3 plus 1 by 2. Alright, here's the interesting thing. Divide this quantity with this quantity. And you get something like, this is almost n square by 2 divided by, this is almost n square by 9 into 2, which is 18. Okay, so n square and n square cancel each other out, 2 goes down. So this comes out to be around 9. So this quantity is 9 times of this quantity. Alright, so the ratio is 1:9. On the other hand, what is the amount of effort that you need to put in over here? 30% of the numbers. So 30% of all numbers. So 3:10. The amount of effort you put in here is 10 units. The amount of effort you put in for 30% of numbers is 3 units. The amount of output you get, the importance over here is 9 units. The amount of importance you have over here is just 1 unit. What does that tell you? It tells you that for more effort, this ratio is smaller. For more effort, you are getting lesser value. Which means you should get rid of this. You should get rid of the first 30% of numbers. And of course, this is not a hard and fast rule, 30%. But what you're seeing is that to get a reasonably good answer, you don't need the first 30% of numbers. You can get rid of the first 20% also, that's also fine. In fact, the ratio there will be even poorer. Okay, so that's one of the key insights which was there in the contest, where I have the array B given to me. And what I would do is I would sort the array and take the first 30% elements and just dump them. I didn't care. I would take a copy of this array and work only with this. 70% of the elements are giving me a large part of the final sum. So with 70% of the elements, actually you're getting something like 8 by 9 of the answer. Because 1:9, so 8 by 9 of the answer, and that is, let me use my mathematical skills here, approximately 90%. So the solution was approximately 90% good with just 70% of computation. So of course you're not going to use only 70% of the time that you have. What you're going to do instead is increase this from 70% to 100%, and look at your answer going from something like, if it was 9 units earlier, then it will be 10 by 7 into 9 units, which is 90, so that will be around 13 units now. Okay, lots of approximation. How I'm getting to these numbers is also pretty obvious if you think of it for some time. It's 9 units earlier. Your computation power has improved from 70% to 100% into whatever you had earlier, into 9. So that is around 13 units. Okay, so a 30% or more actually. So pretty good answer awaits. Alright. Finally, apart from these things, there are a few additional optimizations which are domain specific. One was, instead of calculating the remainders again and again, I used a 2D array to keep track of what remainder for what b of I, a remainder with b of I. If I'm swapping 2 digits in a, then I was able to compute the new remainder very fast. So that was one of the good things. It was again an optimization. I tried to also make it like a batch. So I would run this algorithm, get some good answers for A, and run it in the second batch, and then so on and so forth. So I didn't use any of the curve fitting algorithms over here. I just used randomization. Right? I'll just say that straight up. I didn't use hill climbing or simulated annealing or genetic algorithms. I just used randomized algorithms and worked pretty well. So this was another thing. I mean, just doing it in batches. And the final thing that I did, which didn't affect too much, but it was pretty nice to think about, was multi-threading. So Codechef offers you multiple processors. What you can do, instead of using just a single processor, which is like using 100% of CPU throughput, you can make it 200% or 400% of CPU throughput, depending on how many processors you have. So use multiple threads and send them to different processors. So you're using all processors. So the computation power of that went up. It didn't increase the score much because there's a curve, and maybe you're somewhere over here. So you'll be stuck at local optima, while over here maybe there's a global optima. But beyond, very close to that are these two big peaks, so you don't want to explore over here. That's the reason why you will probably never get to these points, and you'll be stuck over here. That's a problem with any curve fitting algorithm. So in summary, when we solve challenge problems, we find a base solution, we find a way to search the search space, and then find the maximum or the minima depending on requirement using one of these special algorithms. And then you start optimizing using domain-specific knowledge. So if you want to look at it graphically, this part helps your performance, which means you can plot more points, the curve gets better. The curve fitting algorithm helps you approximate the curve better, so this improves your score. And this base solution just helps you get a solution. So that's it on solving challenge problems. If you want more details, then there's a link in the description below. I'll also put a poll actually for finding out what you want to learn next, which is either data structure or algorithm or any topic which is related to comparative programming. If you have any doubts or suggestions, of course, you can leave them in the comments below. If you want to know about the code or relevant links, then it's in the description. And until next time, see you.